Okay, so this will be one of the first videos in a series on group theory. I have talked about group theory a bit in some of my videos, but this time I'm doing a whole project which will be involving a lot of group theory, and so I just need a revision. And so instead of making one very big video, which is going to cover all the concepts, I'm going to make bite-sized videos. So we're going to start with some introduction, like to what a group really is. So first example that I want to give is the symmetries of a triangle. Or okay, so let's start with something even simpler. So if you are from the same background as I was 2 years ago, you might be very familiar with complex numbers. So consider the roots of unity. Let's say the fourth root of unity, which is iota. So so on the complex plane, we have these numbers: 1 iota minus 1 minus iota. uh, and so what we can do is we can consider the multiplication between these elements. So I'm just going to make a set out of these elements: 1 minus 1 iota minus iota. And just consider the multiplication between each of these elements. So I'm going to make a table for that. So it's a multiplication table. So I'm going to write it like this: iota, then minus 1 minus iota, and 1 over here as well: iota minus 1 minus iota and 1. And then you can fill this up. So you're going to have minus 1 and then that times of iota. So just keep multiplying by iota essentially. So we'll just have minus iota, then 1, and then iota again, right? Over here once again, so it's just minus iota and then keep multiplying. So it's just 1 iota and then minus 1. And so this is 1 iota minus 1 and then minus iota. And this will be iota minus 1 minus iota. Yeah, and 1. Okay, so notice that the operation of multiplication, right, which I'm going to represent by this dot symbol, along with this set, it has some nice properties. This object has some, so I'm going to call this object as I don't know, let's call it something G, right? So this is the ordered pair of a set along with an operation, a binary operation defined on any two elements of this set. So it has some nice properties. So notice that, so I'm just going to sort of highlight these, like, yeah, right. So it has a nice properties. First, notice that this element 1, it's the identity element for this binary operation iota. So you take any element, so A from this set, right, and you multiply by 1, you get exactly the same element. And then if you left multiply by 1, you also get the same element, right? Now also notice that every element has its inverse for this binary operation. So what I'm saying is that for every element A, which is a part of this set, which I'm just going to informally call G, although G is this ordered pair, I'm going to also think of the set itself as G. Slightly sloppy notation, but whatever. What's going to happen is that there exists an inverse, right? So let's call it some other element B, such that B times A is A times B is just the identity element 1 in this case. So I'm just going to mark the identity element with this shade everywhere. Right. So right off the bat, you can notice that for every element you have some element which multiplied with it gives 1, right? Also notice that none of these two elements are the same. That is, for every A in G, you never have two inverses, right? And this is kind of easy to prove. So if there were two inverses, let's say B and C, then what should happen is that A times B is identity, which is also like B times A, and then A times C is identity, which is also C times A. But notice that A times C can be written as A times the identity times C, but then that's like ABAC, right? Because BA is E, but then AB and AC, so that's like the identity, right? I probably shouldn't be doing this. Yeah. Yeah, right. I shouldn't be doing this. Okay, let's not go with that. So, okay, let's think of it like this. So, if this sort of happens and B is not equal to C, then what's going to happen is like B you multiplies by the identity. You can write that as B times AC, but then B times A is just the identity once again, because like the way it's defined. So it's just E times C. I'm writing E, it should be 1. Sorry, E is the usual identity that you see in multiplicate in any group, really, everywhere. So I shouldn't say E over here, I should say 1. But anytime you see E, feel free to replace it with a 1, provided we're not talking about like fields or something like that, which is probably I'm not even going to talk about that any soon. But yeah, so what essentially you get is that B is equal to C, because obviously something times 1 is just that thing, and 1 times something is just that thing. So this is like a contradiction. So clearly you can't have two different inverses. So there's always going to be unique inverses for this sort of a structure, right? You also notice that this operation is associative, right? So if you do A times B and then that times C, that's the same thing as doing A times B times C, right? And in this particular case, the operation is also commutative, but that's not necessary. You could consider some other operation, say like matrix multiplication, and then it's not necessarily commutative, right? And we will consider a simple, or I should say easy group where you won't have this commutativity thing. But what you're noticing is that this structure has these 4 properties. Firstly, associativity of the operation. So my associative, I don't know. There's an identity, so 1 exists, right? For all A, its inverse exists, right? And then it's also going to be unique, like we just proved that, really. Also also what's going to happen is that the multiplication between any two elements, that thing, so if these two elements are in our set, then the multiplication is also going to be in our set. And you can notice that from this table. This table is what's called the Cayley table for any group. So this is the group, and this is the group's representation as a table. Yes. So now let's go to a slightly better example for a group, one where you don't have commutativity. So let's consider triangle, and it's not like just 3 lines. It's more or less sort of like a cardboard cutout, right? So it's like I shouldn't say 3 dimension, it's more like a paper like cutout of a triangle. So one side is like shaded black, one side is shaded white, right? And then let's say you have marked the corners as 1, 2 and 3. Yeah, and so this is also 1, 2 and 3. So now what I want you to consider is in how many different ways can you sort of take this triangle, like and put it back onto the ground, so that the triangle sort of fits onto itself. As in, so if this is how the triangle original is, you do something to it, some operation, like I don't know, you move it around, whatever you want to do, maybe like flip it or something, and then maybe it comes out like this, that you have a 3 over here and a 2 over there and a 1 over there, and obviously like this is actually going to have the black side on the top, and why that's going to happen, because essentially it's like you flipped it, right? But notice that this can exactly fit into this triangle. Like it can be superimposed onto this triangle, so it's symmetric in a way, like the shapes match, but you know that um, what was originally there is not originally there. Like this vertex is now here, right? So this is the symmetry of the triangle. Now consider all the different symmetries of this triangle. Well, first, there are like some symmetries which are like very easy to understand. So if you consider rotation, that's the symmetry. So first there's the symmetry of like not doing anything at all. So that's the identity symmetry. So it's just 1 2 3, right? There's the symmetry of rotating it once, maybe like counterclockwise, and so this is 1 2 3 like this now. So let's call that as R. So you do an operation R on this triangle and you get this new triangle. You can do this 2 times and then you get something like R squared, right? Because R and R, so that's R squared. And so you're going to have 2 over here, right? 1 over here and 3 over here. And then if you do it 3 times, what's going to happen is that you're going to get the identity symmetry back. Like that's easy to see. Now there's another way that you can do something to this triangle, which is you can reflect along one of the medians. And so let's say that one particular reflection is called S. So let's say it's this median that you reflect along. So this will be 1 and this will be 2 and this will be 3, right? Yep. And you'll see that if this was the white side that's on the top, now it's the black side that's on the top. And from here you can basically get all the symmetries by just rotating this, right? So essentially for this paper cutout triangle, you can either have the black side on the top or the white side on the top, and then in both cases you have 3 different orientations for this triangle, right? So that's everything that can happen. And so the first 3 orientations you already have, like when the white thing is on the top, if the black thing is on the top, this is one thing. Now to get the other 2, you can just keep multiplying by R. So like you'll just have 1 3 2 over there, and then multiply by R again, and so you just have you'll just have 3, and then this is 2 and this is 1, and this is shaded obviously. So essentially you multiplied this by S and then R. So the whole operation you did was S times R, which is like SR. In this case it was SR squared, right? And in the first case obviously it was just S. And obviously you had the normal rotations without the reflection being in there. So it's just the identity R squared, right? And so this set of operations, or you could say, so operations on this triangle, right? Along with the operation of function composition, which I'm also going to write using this dot thing. This is a group, right? So I informally define what a group is. These 4 things which were properties in this structure, that's essentially what a group is. So group is any set endowed with a binary operation where the binary operation is associative. It has an identity which is in the set, and for everything in the set, an inverse is also in the set, and for any 2 elements in the set, their multiplication in a sense, or more like the binary operation on them, that thing is also in the set, right? And so this is actually a very sort of popular thing. It's called the dihedral group on 3 elements for now. So it's basically the symmetries of a triangle. If you wanted a dihedral group on 4 things, it's more like symmetries of a quadrilateral and then a pentagon and so on, right? So it's called dihedral because like it's a 2-sided polyhedron, if that makes any sense, right? So you can once again make a Cayley table for this thing. So this thing is once again called a Cayley table, right? And both ways to represent would be correct. So what this group essentially is a bunch of functions. So this E thing, it's a function, this R thing is a function, R square is a function. And what do these functions do? They take a certain orientation of a triangle and spit out another orientation, right? So if you say take certain orientation like maybe 1 2 3 like this for the triangle, and then multiply this thing by R or apply R on it, that's going to spit out 1 2 and 3 like this. So easy to see, right, what's happening. So what we can do is we can say that this group is acting on some set. So that set is more or less all the different ways you can have a triangle, or you could also think of the set just being the vertices, right? So the orientation can be completely determined using the vertices. Yeah. So essentially, you have the vertex labeled 1, 2, and 3. You consider a set S with these elements, and then you have this function which like sends 1 to 1, 2 to 2, and 3 to 3. You could have this rotation thing which sends 1 to 2. I think, yeah, that's how it is. 2 to 3 and 3 to 1, and other stuff, right? Reflection which does something weird. But what we are going to say is that this group D3, it acts, I don't know how to write this. I think this is how you write it. It acts on S. And so every element in D3 is essentially a function. Now every element is, so G in D3 is a function. So G goes from S to S, right? And this is not just any function, it's a bijective function, right? So for every element in S, it's going to map to a certain thing which no other element gets mapped to, right? And then it's S to S, so like, yeah, it's surjective as well. Cool. So far you have the notion of a group action. So a group action is basically like the element acting on some object that changes the object, right? And so you compose these functions, and that's what a group is. Cool. Okay, so that's good for this video. I'll carry on the next time. See you guys in the next video.